Hello, everybody. Welcome to my presentation about POWER9 support in coreboot. This is the agenda for this presentation. I will shortly introduce myself, who I am, and what I do. Then I will describe who is involved in this project and why we chose coreboot. We'll present some basic use case for the POWER9 coreboot port. And I will shortly describe our development roadmap we have anticipated, and the eventual future plans for another features in development. I will also introduce you to Dasharo, what it is, how we will validate our firmware on the open power with our remote testing environment. We'll also describe what is the Dasharo trustworthy computing, and how anybody can help and contribute to the project. I will also show some short demo, how we launch the coreboot on the open power, and some extra bonus slides. So who I am? I'm Michał Żygowski. I'm a firmware engineer and free and embedded systems consulting. I'm a Braswell SOC, PC engines, and protected platforms maintainer in coreboot. I'm mainly interested in advanced hardware features and firmware, coreboot, and various security solutions. So to begin with, what is firmware and how it is related to various instances? So firmware is a class of software that helps to initialize the low-level silicon and pass the control to the target operating system or software. And many OEMs and ODMs depend on the firmware to provide secure and compatible high-performance environment for customers and operating systems, while cloud providers depend on the firmware to use advanced platform security features and provide some trusted and hardened virtual machines in their infrastructure, while service providers depend on the firmware to efficiently leverage the security and runtime management capabilities in their solutions. So other analytic companies and AI and stuff depend on the firmware to fully utilize the underlying hardware and tune it to particular workload. So as we can see, we can differentiate through the firmware for various market sectors. And yeah, what is the goal of the firmware? So firmware has to initialize the necessary hardware as fast as possible and boot to the operating systems. Preferably for open source, it is a Linux. This is the goal for both open power firmware and coreboot, to initialize the hardware as quickly as possible and just hand over to the target software. So coreboot was always a good replacement for some alternative firmware, and mainly for various open firmware implementations like RISC-V. The first open firmware implementation for RISC-V appeared right here in coreboot. So now it is the time for the open power. Of course, we may use the emulated Power PC64 in QEMU, but that's not fun even in the slightest bit. Nothing can really replace the real hardware experience. There are companies that work hard and keep pushing the x86 silicon vendors for more open firmware. One of the main pioneers is the Google, which promotes the coreboot with their Chromebooks devices. Coreboot is also used by Tesla, Siemens, and probably by many other companies we are not aware of. And yes, to other companies also we can count the PC engines or Lenovo laptops, Supermicro servers. Moreover, coreboot is quite well recognized brand for open source firmware already. It has established its brand for over 20 years. And is probably the top 2 in the most recognizable firmware solutions right after UEFI implementations like Tanacore and EDK2. That means if Power would be supported by coreboot, it should become more popular as well. Coreboot is also known to be super fast and lightweight, so the boot speed should be lower compared to open power firmware. For example, the equivalent of coreboot functionality, which is called hostboot in OpenPower firmware, takes about a minute to boot. The main programming language in the coreboot is C. It is much simpler and lightweight than the C++ used in hostboot and other OpenPower firmware components. Although the C lacks many advanced features of C++, exceptions, runtime, type information, objective programming, etc., but it is much faster. Coreboot also supports many architectures. One firmware can be run on all platforms with the same security model. So one firmware to rule them all and one threat model for all. And of course, it is easier to find coreboot developers than OpenPower firmware developers. And yeah, who is involved in the project? So Insurgo Technologies, Libris Open Technologies, is the initiator of the whole project, as well as its main sponsor. Insurgo sells their own product called Privacy Beast X230, a custom refurbished Lenovo X230, certified by CubesOS. It contains open source and hardened firmware implementation based on coreboot and heads. The product is also known from the secure process of firmware ownership as a first-class and first ever done in the world mechanism to regenerate secrets and mitigate supply chain attacks. However, X230 is quite an old laptop, almost 7 years, and there seemed to be no possibility to move to a more modern one. Why? Because x86 architecture is bloated with many binary blobs responsible for hardware initialization. And this likely will not change in the future. This is why Insurgo looks far ahead and turned their eyes on the open hardware architecture, which is OpenPower. Insurgo, together with FrameDev, want to promote the open firmware solutions, and as a fellow colleagues in a single profession, cooperate to make open and fully ownable hardware accessible to everyone. FrameDev, with much experience in the firmware field, will be responsible for porting the POWER9 architecture to coreboot, with Talos 2 and Talos 2 Lite as reference platforms. FrameDev also will offer products based on POWER9 platforms and software firmware and firmware development services and support. So FrameDev loves coreboot. That is why we want to do the port. We have a quite strong presence in the boot firmware for network compliance and firewall devices. We have ported firmware to PC engines, APU routers, the protective vault platforms, etc. We are quite experienced also with SRTM and DRTM firmware development thanks to the Trench Boot project. We did some TPM 2.0 enabling for the Infineon TPMs in coreboot and CBIOS. We also did the implementation and enablement of IOMMU and for the PC engines APU too. We did some low-level validation integration for bits and chipset payload in coreboot. We provide also open source firmware trainings and workshops. And we organize, for example, the Grab and CubesOS mini summit. And we are quite active in the open source firmware community for over 5 years. So how our example use case would look like when we have coreboot on the OpenPower machine. So we also start from the reset vector, but it looks quite different in the OpenPower. Before the main cores are launched, there is a secondary processor called self-boot engine, which does some initial preparations and initialization before launching the main core. And when the main core is released, it jumps to the coreboot boot block. Then we go through the typical coreboot stages like ROM stage, run stage, and then the payload. For now, the difference is that we need to launch like 2 payloads. So the first payload is skiboot, which also includes some necessary hardware initialization and provides API for proper operating system operation. And then we can jump to our favorite payload, which typically is a Linux, like Linux kexec based bootloader like Petit Boot or Heads. In our model, we will prefer the heads payload for the security and other stuff. So this is an approximated roadmap for the development. So we managed to run the coreboot boot block at the end of September, and now we face the ROM stage support implementation. It is quite complex, as already described soon. That is why it takes much time and is estimated for many work days. So we also have some plans to port Zen to Power, as you can see, which I will also mention later. The target final date is, for now, it is 13th of June, but I anticipate it will be quicker. So how the coreboot boot flow compares to the Open Power firmware boot flow. Let's review the boot flow for x86 and coreboot. So the boot block is responsible for setting up some temporary memory and cache, set up the stack to run C code, and perform some very basic hardware initialization and set up the debug interface. Well, for POWER9, it will be equal to the iStep 6, which is available in the IPL boot flow, which I have linked in the slide. It will be responsible for handling the state left by self-boot engine, set up registers to run the C code, and set up the debug interface. For the ROM stage, this is much more work than a coreboot does for x86. For x86, we typically perform necessary hardware initialization to train memory, set up and train the main memory, and set up CBMEM. So for POWER9 boot phase case, it is many more hardware initialization. This covers the iSteps 7 to 14, and we have to do various configuration of Nest, Fabric, Power XBus, SMP initialization, and then at the end the DDR4 initialization. It is quite much code to implement in the ROM stage. And at the end, of course, we also set up the CBMEM. For the post-car, we don't anticipate any work in the POWER9 for now. For x86, it typically tears down the temporary memory and prepares to run from the code from DRAM. So the RAM stage, typically for x86, it is responsible for initializing devices, constructing SMBIOS and ACPI tables, finalizing hardware initialization, checking for OSFC, and loading and executing the payload. For POWER9, it will cover a few iSteps from 15 to 21. It will also be responsible for device initialization, and also it will construct the device tree for operating system consumption. Yes, the Open Power hardware honors the device tree for launching the operating system, similarly as ARM architecture. And we also load and execute the payload. So the differences in payload would be that we have a SKIBoot as a first stage payload, as I mentioned here, which is necessary to initialize the rest of the hardware, to train the PCI links, and it exposes the Open Power abstraction layer for the operating system. And the second stage payload would be the real target payload we would launch in normal coreboot boot flow. So it would be a petit boot or other equivalent KX-based payload like heads. So in order to leverage the advantages of coreboot's flexibility, all hardware initialization should be done before jumping to the payload. So then anyone could run any payload they want. Developing firmware is one thing. Keeping it up to date, either for security reasons and other improvements, is another thing. As the official consultants for Linux Foundation FWPDL-VFS, we also plan to enable the Open Power-based machines firmware update in this project. FreeMDEV also got a grant from the ANNOLNet for porting FWPD to BSD systems. We'd like also to become the independent software vendor for Open Power, not only in the firmware field, but also in the user space. We have Linux experts on board, which together with our firmware specialists will prepare a solution satisfying anyone's needs. Everything is a part of our Dosharo product family, The Dasharo will be described soon. We have just been accepted in September as a silver member of the Open Power Foundation. There is more and more interest around the Zen port for the POWER9. Interesting parties are gathering and discussing the roadmap now. We also would like to boost the knowledge about coreboot and open power with various trainings to widen the group of specialists and attract the world with power architecture. So in order to really leverage the advantages of coreboot, we also need to port the skiboot, hardware initialization to coreboot, to have a real coreboot booting model compliant stack with open power. So when it comes to Zen port, it has been recently been discussed on the Zen Devil mailing list, and we have various meetings right now ongoing, and we discussed the design of the Zen hypervisor for power. There are many interesting parties in this project, like IBM, FrameDem, Citrix, Fates, Fantosh, CubesOS. We're keeping to get close to the dream of running CubesOS on open power. You can also refer to the other issues set up on GitHub of CubesOS, which also describes some challenges and information about Zen port to power. So when it comes to Dasharo, Dasharo is a set of productized services with open core and software as a service products which help to provide scalable, modular, easy to combine open source BIOS, UEFI, and firmware solutions. This is a FreeMDEP firmware product which consists of 4 basic modules. We have a security module which gathers various security features to make your hardware more trustworthy, a performance module which provides some optimization features to boost your performance or adjust the performance to the customer's needs. We have also the compatibility module, which provide the various maintenance features, automated regression testing, etc., etc. The marketing module is designed to raise the awareness of the brand and the customer value features. So the validation in our lab for open power and any other Dasharo-enabled platforms is done with our remote testing environment. We have quite advanced testing infrastructure, which is presented in the diagram. So each platform is connected to an RTE, which is responsible for power management of the platform and the flashing and gathering various logs. And the Dasharo Trustworthy Computing. Dasharo Trustworthy Computing is a special distribution of Dasharo for the Open Power Talos 2 platform. It contains various system features like the Dasharo operating system deployment, provisioning features like equivalent to SafeBoot, firmware ownership, and heads payload. We offer various firmware recovery methods, firmware updates with LVFS, FWPD. We want to have a target CubesOS operating system. We also offer the remote attestation with DRTM, Trenchboot, and Dasharo attestation server. As a base of any Dasharo product, we also offer the long-term maintenance with regular signed releases. Of course, each release will be covered with a wide regression tests, which results will be also delivered with each release. So the Dasharo Trustworthy Computing shall include the following software stack. So as in typical open power firmware, we start from the cell boot engine, which will then launch the coreboot, and then we jump to the required skiboot and heads payload, which in result will load the CubesOS securely. So how anybody can help and contribute? Well, whole development is open source and available on our GitHub. We still need some documentation how to start and build firmware, since we are doing the verification of the build system, which is by default provided by OpenPower firmware, which is OP build. And if you have an hardware, then simply join us in development. We are open to collaboration. Alternatively, we will also give you some remote access to the hardware if you do not possess Talos 2 or Talos 2 Lite. So if you are experienced in OpenPower and POWER9 architecture but cannot develop, well, your knowledge alone is also welcome. We may have many issues and questions with regards to the hostboot code and other and the low-level silicon stuff. So I have prepared also some short demo for the Talos 2, which is booting the coreboot boot block. So I will show you some Skinemo recording. How does it look like? And yeah, we are connecting to the BMC on the Talos 2 machine, and we will flash our coreboot ROM to a special partition called HBB. And now we will connect to the we'll power on the platform and connect to the console. So it takes some time for the platform to power up, so we don't lose any locks. So we will have a chance to see how the coreboot is booting. Yeah, and that's basically it. There's not much here because there's on this video there's a boot block which, in fact, does nothing for now. So that will be it for the demo for now. During the development of the RAM stage and DDR4 training, we have encountered various different issues or funny bugs in the code. We have encountered various issues and funny bugs in the code. And on these two fragments, you can see that point 2 says that reset should be either driven low or high. So which is it in real? We don't know. Second fragment says that up is down or down is up. Another point to explain which it should be the real name, or maybe just the comments are replaced with them between them. And a fun question: how many dual inline modules are in the dual inline modules? So it appears we have only one DIMM per module. Wow, surprise! And the last one is quite it's quite different. So there are some files in the host boot code that are made from so-called init files. These init files describe very complex procedures which are written by the silicon designers itself. Imagine this just register read-write sequence which has to be performed to initialize some hardware. And in these fragments of code generated by these init files, each literal is defined with some preprocessor directives or simply variables. So whole files are simply, for example, like this. So we have literal _1, which in real expands to an integer equal to 1. And in this fragment of code, we see that we have if condition and else if condition. If you look a little closer, the expressions which are inside the brackets are exactly the same. So no matter what is the attribute EFF DIMM type in this array, the executed code will be the same. So what really should happen here? Well, we don't exactly know. And yes, that would be everything for my presentation. Thank you for attending, and I'm open for any questions and discussions. Thank you.